Right, great. Thanks very much. Firstly, yeah, I want to thank the organizer for having me here again. In fact, I present a version of this in London, and thanks for the very good comments. I hope it has improved a lot. So you see, this is joint work between myself, Abhimanyu Gupta, who's now at Queen's, and a couple of friends from Brazil. Um, and as the title suggests, it's going to be something on estimation of dynamic discrete choice models. And I'll then start with the motivation. For the students, especially who are attending the summer school, what you would have noticed is that computation is an important thing in this literature. And in terms of estimation, you can go full solution or you can go what I call CCP. I'll describe what that is in a moment. So I would say with a lot of respect, the different options depends on your pain threshold. So I'm very weak. I can't handle full solutions. Like Bob, Victor, they can do both. It's okay, but I can only do, the lower pain threshold stuff. And so I call the alternative approach to full solution as CCP. And this is something that I don't normally call an estimation method, but I'm taking this from Bob's paper in Diagonal and Miller, where they describe the CCP estimator as one in which you exploit the relation between the difference in value function in terms of the CCPs or the policy function and the transition probabilities. And you also, in order to apply the CCP estimator, you must be able to consistently estimate the CCPs at all states. And you can either do this at the beginning or eventually. And what I mean by doing this at the beginning, I mean that, well, if you have a consistent non-parametric CCP estimator, then you can apply what is called in the literature as a two-step estimator, where well, you just use the non-parametric CCP as your first step estimator, and then you just estimate the parameter of interest 2 steps. But you can also iterate or do other things, and there are various benefits that you can get with that. But if you do that, then to me, I don't call this two-step estimate, but then they're classified as CCPs, right? So like Victor has a paper on this, of course, you can improve finite sample property and get efficiency. And in the case of unobserved heterogeneity, if you iterate, you can also handle that also. And this is really the gold standard in terms of how to handle unobserved heterogeneity, in the sense that I remember when I was a graduate student or before Diagonal and Miller came out, when I present my work or I was at a conference, I often get questions about, well, can your two-step estimator handle unobserved heterogeneity? And since the paper came out, I haven't been asked that question again. So, but then it's not a two-step procedure, right? So now what I'm trying to do is try to do the two-step procedure when you have unobserved heterogeneity. And the reason for caring to do this is that relatively a two-step CCP estimator is computationally lighter generally. And potentially the lightest version, I think, that you can have is when you have a closed form solution, right? A closed form estimator for this. So which is what we're going to show that it can be done. And also in terms of estimation of games, when you iterate, sometimes the iteration can lead you off to an equilibrium which didn't generate the data, so that can cause issue in games. So there is reason to pay attention to how, or think about if we can extend the two-step approach to to handle unobserved heterogeneity generally. The issue, of course, is that if you have unobserved states, then it's unclear how can you consistently estimate the CCP initially. And what we propose to do is to just estimate the hidden states, because here we are dealing with a finite state situation. And unlike Bob's paper and also Victor's paper, which also deal with unobserved heterogeneity also, but what they do is solve classification, because they embed a mixed model in the likelihood framework, then they estimate that. But my approach, I'm doing hard classification, where I'm going to estimate these hidden types, and then when I have this latent states or latent types, then you can just do two-step estimation procedure. And I'm going to show that under very weak conditions, we can get our coefficiency estimators for the structural parameter of interest. And our coefficiency here means that you can estimate these parameters as well as if you know what the latent states are. And we allow for various types of heterogeneity. It can be time varying, time invariant. And when it's time invariant, we are also able to distinguish between heterogeneity that comes from differences in payoffs, differences in transitions, as well as the multiple equilibria. And we are also able to estimate the number of latent types, including distinguishing whether these things are coming from different sources, whether it's multiple equilibria or pair of heterogeneity. And then I'll illustrate how much time I get in doing this. Okay, so that's the motivation. Literature, I don't want to spend time talking about this, but happy to talk about these things afterwards, other than wanting to highlight that, yeah, so we really want to build on this literature where Kasahara and Shimosu, Agri, Gabiria, and Mira, they show how one can estimate models with time invariant types. And Hu and Sham, Kalusidi et al., they consider the case when you have time varying types. And Ashira, Gono, and Miller, they can handle both types. Right, and the plan of the talk is the following. I'll describe the model assumptions and proceed as follows. So here is the typical framework before I input unobserved heterogeneity. So here, this is just standard assumptions that we would have seen in the first day or the first lecture of the summer school. So there's nothing to say there other than I'm imposing the payoff function is additively separable, and the part which corresponds to the observables is linear in parameters. And this is actually not restrictive because A and X are finite. So you can think of this as a non-parametric restriction. Although you have to impose something because we know these models are not identified otherwise. But then what do you impose or what you normalize? That's not what I'm trying to answer here. I just assume you make that decision and then we deal with that. And of course, this is the conditional independence assumption. And then we assume the distribution of the econometric error term and the discount factor to be known. But if you want to know how to relax those, then you can look at these papers. And to have unobserved heterogeneity, I'm denoting this by C and D. So C is going to be the time invariant type, and D is going to be the time varying type. And C and D are going to be finite. They have finite support. So you see that they enter the payoff function in a fairly general way. So there's interactions that we allow for C and D. And then in terms of how this enter the transition probabilities, we assume that the time varying types would only enter as an exogenous Markov process. So you can think of this as a common macro shock, for example. And if you don't have the time varying type, if we ignore this H part, then this is just the same as the standard framework that we have on this page, other than the fact that we can have Q and G to depend on C. Okay, so this is the type of unobserved heterogeneity that we are allowed to enter our model. Then, so I point this out with slight embarrassment because I think people who work in this literature know that if you have linear specification of the payoff function, you can exploit this linear structure, right? And in particular, it can be shown that the structural parameter of interest that we saw on the previous slide can be written completely as a function of the CCPs and various transitions. Therefore, if you observe everything, meaning A, X, B, and C, then you can estimate whatever that you need to, the CCPs and this transition law using the, say, the frequency estimator. Then these are consistent, and then you can therefore get a closed form estimator for theta C. But if you don't observe C and D, then you can estimate them, which is what we propose that you do. And if you do that, then you get a feasible counterpart of this. And we're going to show that the estimator that you obtain through clustering can behave as good as this estimator as reported. Right then, in the DSE conference in London, I presented the version where I identified the time varying type. So I'm going to focus on how one can estimate the time invariant types. But then I'll look at the other case as well. But I'm going to provide more details on this particular case. So here I'm assuming that A, X, and C are finite, and the cap A, cap X, and cap C denote well, A plus 1 would denote the cardinality of set A, but X and C denote the cardinality of the set X and set C. So for the time being, I'm going to assume I know how many time invariant types there are. Then I'll deal with estimating this later. Then we're going to observe actions and observable state X, and that's it. And what we want to do here is we want to learn of the latent time invariant type from the data. So what we can do is that for every individual or firm agent M, and in the game case, it would be market M, then we can compute the CCP, the estimated CCP, using time information for every M. So we can do this for every M, and then the idea is to cluster this object. And this is going to tell us about, well, which M belongs to one of these types. So this is the basic idea behind how we want to identify the which time invariant types that each M is in. Then if we have an estimated CCP for a particular action and state X, then we can vectorize this into this object. And this is what we want to do k-means clustering on. So the procedure of the k-means clustering with D types is just partitioning these estimated samples now into C clusters. And the idea is that for each M, we want to assign Q hat M into the cluster that this vector is closest to the center of that cluster. And then the k-mean objective function just computes the within cluster sum of squares is what this thing is. The minimization here puts the Q hat into the cluster that is closer to the center. Therefore, the input of this objective function is just a concatenation of centers. Then the assumptions that we're going to impose here are the following. Firstly, before I mention that, I want to denote the true CCPs that we don't see by Q0. And the assumption that we're going to assume is that across M, the assignment of types are IID. And the second condition says that conditioning on CM, then the process A and X is a nice process. It's stationary, satisfies some missing condition. And this is these are very weak conditions, by the way, because we are essentially dealing with a finite Markov chain. Therefore, you can have these conditions holding with very weak conditions. And then we just say that different CCPs that we're trying to estimate, they are different. Otherwise, there's no issue about heterogeneity. Then under these conditions, it can be shown that if log M is little o t, that means log M grows much slower than t. Then we can show that our estimated CCP that doesn't specify the type that M belongs to consistently estimate the true CCP uniformly across M. So this is what lemma C1 says. Then lemma C2 says that the estimated centers, which are essentially the estimated CCP profile that minimizes the k-mean objective function, is a consistent estimator of the true center, which are these Q0. So the notion of consistency is written in a slightly unusual way, but that is just to accommodate the fact that these k-means objective functions, they are invariant when you change the label of the centers. This is a matter of label permutation invariance, but otherwise it's just standard notion of consistency. Then theorem C tells us that, well, then as long as log m is little t, is little ot, then the misclassification error from k-mean clustering go to zero extremely fast. It goes to zero faster than 1 over m raised to any power of rho. And the intuition behind this is actually geometric. And it's because since we can estimate the underlying CCP uniformly well, then we know that with very high probability, all of our cube hat would be close to the true center. And it can be shown that if that is the case, and if the true centers are also close to the estimated centers, then you don't misclassify. It's just a geometric fact that when they're within certain neighborhood, then you don't classify. Therefore, with high probability, we're going to uniformly correctly classify types. And once we have that, then we can transfer this to think about, well, what we need to do for two-step estimation. That means we then need to estimate the CCP, right? Then we want to estimate the joint probabilities, conditional probabilities, and so on. So corollary C says that if you take any bounded sequence SAT M, so you should think of this SAT M as indicator function of actions and state X. Then this object here could be an estimator for probability of action A being taken when state is X, and then DM is being estimated, right? And for it to take value C. And this is the infeasible counterpart. And then the estimation error rate inherits the super fast rate of convergence that we had from theorem C. Then under these conditions, it can be shown that the CCP estimator that you get from this, the estimation error from using the feasible estimator relative to the infeasible one is going to go to zero at a super fast rate. So this is how we get Oracle KPP form. So can you out there? Right, number of markets and number of. So M and T need to go to infinity here. Well, you see what T doesn't need to go to infinity faster, right? So log M is little OT. Therefore, M can go to infinity much faster, but the log of M can be slower than T.
I see. So I'm just trying to think, like, as a practitioner, potential who's interested in applying this methodology, like the number of periods that would be
you see in the simulations, I guess. But what I want to say also, imagine like M is like 10 to the power of 3, right? So log M is like 3, yeah. You can think of it. So anyway, so if you're happy with this, then doing the time varying states, we can deal with that in an analogous way. So for each time T, then little t, then we can use information across M to estimate the CCP, right? And when we have this type of CCP estimator across T, then we do k-mean clustering on this. And assuming we know that there are, say, there are D time varying types, then we have completely analogous results to what you just saw. But now with respect to the time dimension, so in terms of the assumption, we're just assuming that DT is a stationary mixing process, and then conditioning on DT, A and X are IID, and that's it. So other than that, there's nothing going on, and then we have complete set of analogous results that we would have a very fast vanishing rate for the misclassification error, and then we get all these Oracle results. And if you want to combine both assumption C and D together, you take the union of them, Then we can also deal with the case when you have both time varying type and time invariant type as well. But of course, you need to do two clustering, right? One with just R hat and one with the Q hat. Then you identify the time invariant types and the time varying types. And theorem CD says that if log M is little ot and log T is little om, then we have both of the results that we just mentioned. And just to emphasize, log M is little ot and log T is little om. These don't contradict each other, because here it just says that, well, log M is smaller than T, and here it says that T is smaller than e to the M. Right, so this is not restricted. Whereas the results I had in London, we were working with the different proof techniques, and I was working with square root of M is little ot and square root of T is little om. So it was much more restricted then. So this is a much more general result than previously. Then more time than I expected. Okay, that's good. Then moving on to how we estimate the number of latent types. So previously, I assumed that we know the number of types, right? So we know how many terms to do the k-means with. So to estimate the latent types or the number of latent types, then we propose a BIC type information criteria. In particular, this J hat function requires you to specify the number of types that you want to have a quantification of information for. And it consists of two terms. So the first term is a measure of fit, and that would be the value that you get from the k-mean clustering. Okay, so here we're just focusing on dealing with the time invariant type, because I want to talk about multiple equilibria, I think. So this is the framework that I want to look at. So in this case, W hat here is the value that I would get from doing k-mean clustering on the estimated CCP across little m, across players, or across individuals. Then I would have a penalty term, which is lambda m times the number of types that I'm considering. And I'm going to require lambda m to be positive. And if assumption C along with log E equals little ot holds, so which is something that we assumed previously, additionally, if R lambda m satisfies this condition, then it can be shown that our model selection would be able to consistently estimate C. And the intuition behind this is, if you think about minimizing this type of objective function, when you're using the infeasible W, meaning that suppose we observe the true probability rather than having to estimate it, right? Then in that case, we know that if you choose NC to be C or larger than C, when you eventually observe every state, the value of your objective function is going to be exactly 0. Then in that case, you would never want to overfit as long as lambda is positive, because then you get penalized by that. Therefore, you would not overfit. You would also not want to underfit, because if you underfit, it means that the limit of this objective function, assume that we know what Q is, then you're not going to get the perfect fit. Whereas if you choose C or more types, the limiting objective function is going to be 0 exactly. Therefore, you're not going to underfit either. And this condition here captures the estimation error that we use to replace the infeasible through probabilities with the estimated one. So as long as the penalty term dominates this, then it doesn't affect the infeasible argument that I just. So this allows us to identify the number of types. Then suppose you say that, well, in a game, especially if you have, let's say, C types in the data, but then, you know, the composition of these C types can come from different sources. So I was just browsing through Victor's very nice paper in QE 2019 earlier, where, so this could come from multiple equilibria. So this could come from people just having different theta, right? So suppose we want to distinguish between heterogeneity that comes from different thetas versus multiple equilibria, then what you can do is you can then cluster the estimated theta. And that would, under these conditions, which I don't want to repeat the same story, it identifies how many different thetas you could that you have in your sample. Yeah, so here is a story that suppose there are J and underlying theta type, and then for each little J, then in the data there could be 1 plus little kj possibilities of what's happening. So if this little kj is 0, then there's no multiple equilibria. But if little kj is positive, then that's the number of multiple equilibria that you have. And I mean, this idea can be extended to also deal with the case that if you want to know whether heterogeneity is coming from the transition stage, for example, then you cluster the estimated transition probabilities instead. But the same idea applies. All right, so I have 3 minutes left. And for the simulations, then I'm going to look at variation of Pessendorfer and Schmidt-Dengler's setup, which is the same setup that Paul used. So as Paul mentioned, there are 3 equilibria in this game. And then, so this allows us to explore different possibilities. And then we will estimate this using the feasible estimator with the closed form procedure that I mentioned earlier. So what we looked at when there are different theta types of theta 1, theta 2, and we also looked at the case when there's just additive time fixed effects only. And we also looked at the case when there's only 1 theta, but there are different equilibria, and then the combination of these things. So I'm going to be very selective in choosing this because there's just too many tables to look at. But overall, though, what affects performance, of course, it depends on T and M, and also how well separated the true underlying probabilities are. Just to have an idea, if we look at the equilibria that the Pessendorfer and Schmidt-Dengler's game generate, there are 3 equilibria. Okay, so the third equilibrium is the symmetric equilibrium. So what you see here is a slightly more precise version than Paul's because I have 3 decimal places, and this is important. And you see here that equilibrium 2 and 3, they are very close. So these are the probability of player 1 entering when previously both firms were out of the market, and this is the case when firm 1 was out of the market, firm 2 was in, and this is when firm 1 was out of the market, firm 2 was in, so on and so on. But you see that if you compare these vectors with these vectors, they're rather similar, right? Okay, and this then we're gonna get a worse estimator for when we have both equilibrium 2 and equilibrium 3 together. And yeah, we also look at another theta 2 that has a single equilibrium only, apparently. Okay, so let's see. I think you cannot see this very well. So this is when we have market type heterogeneity through theta only. So theta 1 and theta 2, and I use the symmetric equilibrium to produce this. So I think you should only look at the last 2 columns. The last column, CE percentage, that's the classification error rate. Okay, so we see that with M as 500 and T as 10, the misclassification error rate is 8, 10, something like that. By the way, this mean square error have been scaled up by 100. It's not that bad. Yeah, and then as T increases, then the misclassification rate decreases very rapidly in this case because the equilibria are well separated. And then, in these 2 cases, we compare the feasible and the infeasible estimator, and they are almost just as good. Okay, and then below you have more samples, so things get better, obviously. So time heterogeneity, this is what I presented in London. So multiple equilibria, so this is slightly interesting. So here, the data was generated using three equilibria. And you see here that things are a little bit funny. So we have 8% misclassification error here, 6%, but then 16.7%. I'm not quite sure what's going on here. Having said that, though, the estimates themselves make sense that larger sample sizes, things get better. And the estimators are actually consistent. But then what's going on is when you, and this is the same as when you put in too many clusters than you should. What you're doing is you're just splitting your sample. So you just have less observations in each cluster to do things. So it's not that you just get crazy inconsistent estimate, but it's effectively you just like reducing your sample size. And so this is the case when you have equilibrium 1 and 3, which are well separated, so things behave very well. But in the case when you have equilibria 2 and 3, which is the next case, then the misclassification rate is higher because, then you kind of like can't distinguish between the two equilibria so well. But otherwise, these things make sense. And one last thing before I know I should have finished is about the estimating the number of types. So in this case, we generated the data using two thetas, and theta 1 have two equilibria. Therefore, the underlying time invariant type is 3. Then with a model selection procedure, if you just ignore this C, suppose you look at this column, this column, for example, the mean number of estimated type is correct, and the median is also correct. So the different C is just a different scaling factor that we use. I also have a practical guidance on how you choose this, but I don't have time to talk about it. Definitely looking at me, she's a little bit cross. Okay, and then also more informatively, you can also look at the proportion, the empirical proportions of, how many estimated K was chosen, right? And the one highlighted in yellow is the correct one. And as you see that, when you choose the correct scaling factor, the suitable scaling factor here to be 1.5 or 2, for example, then across various sample size, things get better. And we also get similar results when you try to distinguish between the beta type, which is 2 here, then we also get a pretty good classification results as well. So I conclude that we provide a way to estimate dynamic discrete choice models, which gets you as close as you can to the two-step estimation procedure by doing clustering in the first stage, and we can handle various things, and it can be extended. All right, for the delay. Thank you. I tried.
I think that's totally fine with me because I'm the next presenter and my slide is not super long. Yeah. And I just worry that I won't get everybody to have lunch in time. So I'll try to be quick. Okay, so my name is Jasmine, and I'm going to present a work that builds on Victor and Bob's early work on the finite dependence estimator using conditional choice estimator. So this belongs to the class of CCP estimator. So we start with the problem when we have dynamic discrete choice and state space is large, and one main motivation to come up with finite dependence estimators that we don't want to solve for the value function because of the high dimensionality and the computation burden. There has been previous work by Bob and Pierre Asadiakno showing that the value function of Vxt can be written as the choice specific value function plus a adjustment term, where the adjustment term only depends on a function of the CCP at the current period. And Victor and Arvind also have a paper arguing that you can treat the decision as the players is deciding on the CCP before the realization of the idiosyncratic shock, so that the discrete choice become a continuous choice when you treat the decision that way. So after realization of idiosyncratic shock, you decide on a discrete choice is equivalent to decide on a ex ante TCP decision in terms of the optimal condition. So if these are two equivalent choices, then it makes it possible to derive Euler equation of that. So that's another motivation from that. And the key insight of finite dependence is that if you can have this choice specific value function written as a finite period sum of payoff plus some remainder, usually this remainder contains the value function, but if you plug the value function using Bob's characterization, there's a hope that you can get rid of this value function after a finite number of periods. And there's no need to solve for the value function in that sense. So now the problem is that can we find such weight of getting rid of the value function in the remainder? Okay, so we start with Rust example where we have the bus engine replacement. Decision 1 is keep, decision 2. Decision 2 is to replace, and the model exhibits finite dependence. That's one period finite dependence, and that's a well-known result. So in here is a slight different notation. So Bob calls it one period finite dependence, but in Victor's presentation earlier in the winter school, he calls it two period finite dependence, and I'm going to follow Bob's notation. I hope that. Sorry. Okay. So the renewal action to replace the engine makes the future value function some deterministic value because there's no uncertainty associated with the choice of replacement. Basically, if you're replacing the engine today or tomorrow, will give you the same value function. And the finite dependence estimator that's developed by Bob and RCTs 2011 follows that uses that character. So, and there's an additional paper by Bob and RCTs on the 2019 QE paper. So it basically says that let's let kappa be the conditional distribution over the discrete state after row periods. And conditional on your current state is Z, the current choice is J, and J prime. If there exists a sequential weight from T plus 1 to T plus row, making it the conditional distribution of the state appearing exactly the same after you follow such a sequence of choice, then this model exhibits row period finite dependence. And written in the difference in the value function, it means that you can write the difference of choice specific value function at current period using the finite sum over the future result. So that's their characterization result. But how to find such weight is a problem. With one period finite dependence, it might be easy, but with multiple period finite dependence, it might be tricky and become nonlinear high-dimensional object design. And this paper aims to provide a characterization of how you can find such weight. And just a brief overview of the result, we find almost all the empirical application in economics exhibit two period finite dependence, and with some exhibit one period finite dependence. And very rare are the cases that go beyond two period. And we also provide a mathematical characterization of this result. So that's the contribution of this paper. So we start with a discretized state space X. Sorry, I changed the notation. And we have two decision DT1 and 2, idiosyncratic shock that's additive separable, and the CTP is denoted by this. And if we know this choice specific value function, then we have a one-to-one mapping from CCP to that choice specific value function. And okay, we write the T+2 period conditional distribution of the states as this convoluted summation of the transition probability and the weight choice. And notice that this weight choice, as long as they sum up to 1, that's fine. They can take negative values. And we can actually write this K kappa, the future probability of state appearing at a Hadamard product structure of the weight choice and the future transition density multiply this current transition density. So this is some results that we found. And if you use this structure, solution of weight become linear. And of course, it's linear already for one period finite dependence. But it enables us to conduct a 2-period finite dependence linear weight search algorithm. Okay, so for 2-period finite dependence, we can write the condition, the choice specific value function as in this way. This is W1 weighted T+1 utility plus the W1 weighted adjustment term in Bob's paper, and W2 like T+2 weighted flow utility, T+2 adjustment term. And these sign terms, they can be backed out from the data. They're just functions of the conditional choice probability plus the expectation of the T+3 value function. And how the expectation is taken over is over this kappa term. So this kappa term is conditional on the current state, current decision. What is my future distribution of state if I follow this path of action? And you can have 2 separate paths of weights associated with each xk pair and xl pair. So for each current state, current action, you can have a sequence weight that you commit to. And if you commit to this sequence of weight after 2 periods, you have exactly the same future distribution of states, then this value function got to be canceled out if you take the difference of this V across T and L. So that's this is still the result of Bob's earlier paper. And then we offer a way to solve for this bilinear system using a linear way. So the first step, we assume that this WT+1 is known. Assume that WT+1 is known, then you have this future distribution of states in T+2. And you take that as known, you can write this kappa T+3 as a function of T+2, where this kappa T+2 has inherently WT+1. So assuming that it's known, this function is a linear function of WT+2. Okay, so if there's a linear function, we can solve for WT+2 as a function of WT+1. Then you plug it back. You plug it back, and this entire system becomes a function of WT+1, with WT+2 being solved as a sequence of WT+1. After that, you solve for WT+1, you plug it in back to solve for WT+2. It's kind of like a Stackelberg way of solving this equation system. And in that way, it becomes a linear system solved. And then we characterize the key condition for 1-period finite dependence and 2-period finite dependence using this characterization. We also do that for a general row period. Then we realize there's no much sense than doing in 2 periods. I'll show you later where the characterization. Okay, so for 1-period finite dependence, it holds if there's a F tilde is difference of 2 Markovian transition matrix. And the Fk is the benchmark actions transition matrix we choose. it holds that F tilde multiplied by Fk multiplied by pi F tilde, which is a projection onto the null space of F tilde, equals to 0. So what does this say is that if you have a null space of F tilde, Fk does not vary the null, does not change the null space. Basically, it does not provide new angle information. And this holds in a very specific case where you have just one rank deficiency of F tilde. And this is the case where the bus engine replacement holds. So for the bus engine replacement, F1 is like a upper triangular matrix, where F0 or F2 is a matrix with just ones on the first column. If you take that derivative of these two matrices, it just have one rank deficiency. And then the null space of F tilde becomes all ones, a multiplier of ones. And because Fk is a Markovian transition matrix, it will certainly not vary this if you take the multiplication, because Markovian transition matrix has to sum up to 1. So it will definitely not vary this matrix. And we'll show that as long as the endogenous part of the Markovian transition matrix can be written as some matrix of one rank deficiency, then one period finite dependence also holds. But there's violation if you have a different structure than that. Okay, so I hope I convinced you that many of this bus engine replacement model, terminal exit action model without exogenous states also goes to that. So you just have the like a Markovian transition matrix of action 1 being column 1 of all ones and rest being 0, and F2 being column 2 all ones and the rest of being 0. So in that case, that's also a one rank deficiency case. NJ exit without exogenous shock, surface 2. And the Kronecker structure, if you only have the endogenous part of the transition matrix having one rank deficiency, that goes through this structure. Okay, so for two-period finite dependence, the main condition here looks a little bit more complicated, but it's projection onto the null space of this F tilde, Fk pi F tilde of this matrix. And if you look at that, let's take this as one matrix and this as the second. What it says that is if this double Fk structure does not give you any new information in terms of the angle, then that's going to suffice for two-period finite dependence. And this is a lot less strict than that case for the one-period finite dependence. So one-period finite dependence is kind of restrictive because if you're not looking at something that has only one rank deficiency in F tilde, then that's kind of determined by your luck. You're looking at the null space of F tilde and the rank and the span of Fk. So in that case, that kind of depends on the luck. But for this case, it's the difference of whether this double Fk structure in the middle give you any new information in terms of the direction of the span space. So and this is much easier to satisfy. So after this, I'm going to do a taxonomy of structures of models I've seen, and I just show you how this satisfies finite dependence. So the first structure is the renewal structure, just like the bus engine replacement problem, where you have one rank deficiency of the F tilde matrix, and in that case, one period finite dependence is sufficient. The second type of structure is a lot common in, it's very common in IO, and I think it's also common in labor, is that you have this type of Kronecker structure of the transition matrix, where I call this Fy. This is the endogenous part of the transition matrix, and this Fz is the exogenous part. So if you think about it, that's like in IO, it could be entry-exit with some exogenous productivity shock. And in labor, it could be like the labor choice, the Royce model with some exogenous wage shock. And as long as this part, if you take that part, has a one rank deficiency condition satisfied for across different actions. So Fy1 minus Fy2 has one rank deficiency. Then this is also finite dependence structure, one period finite dependence structure. Okay, so for the third case, that's where we violate the one period finite dependence. Suppose you have a triple connector structure where this one depends on your action, and this also depends on your action. And suppose this has one rank deficiency satisfied, this one also have one rank deficiency satisfied. So easy to think example is that this is your entry-exit status as a firm. And that one has one rank deficiency because the column of each action is being one. And the second shock is some endogenous productivity shock. So if you have been operating on this market, your productivity shock has a higher chance of being higher. Then, and this is some exogenous shocks which we can just take it away. In this case, one period finite dependence will fail, but still two period finite dependence still holds. And we show that using an example, empirical simulation example. And for the first case, I call it block Hadamard. I suppose there's a better way to call it. So the fourth case is the oligopolistic entry-exit game, where as you're standing at the point of each individual player, your transition density depends on some productivity shock, also depends on the other's action. And this other's action depends on the current status of the productivity as well. And in that case, one period finite dependence does not hold. Two period finite dependence structure will hold. So that's all what we got from the simulation. So for renewal and Kronecker with renewal, some the one period finite dependence hold, and that's something we already know. But if we have endogenous productivity shock in entry-exit model, or as in labor model, maybe we have some endogenous wage shock after you commit to certain paths, your wage evolve endogenously that satisfy the triple Kronecker structure. The one period finite dependence does not hold, but two period finite dependence still hold. And we can also allow for like a continuous state as well. So as a comparison for our approach to the Asidiakono and Miller's 2019 approach. So we one innovation we make is that we make this weight solution like sequential, so that the weight solution becomes linear and easier to characterize. But notice that this is sufficient, not necessary condition, because making this sequential, certainly we will give away some information, but the analysis show that this is already enough for establishing finite dependence under many cases. And the solution is easy because we just use this square, and also because we can get rid of the many exogenous states using the Hadamard, using the Kronecker structure, we only focus on the endogenous state. That is much easier to solve in terms of computation burden. And we also covers a broader scope of models such as entry-exit with endogenous shock and games. Okay, so I don't want to brag too much about it. And this is the first example I was working on. That's an example where I have endogenous productivity shock and entry-exit model. So we show that one period finite dependence fail because the previous condition, this one is not zero. If it's not zero, then one period finite dependence will fail. And we show that this condition is satisfied, and also along with some non-sparsity condition with the transition matrix, then we have a two period finite dependence for this endogenous activity shock. And the second case I was working on was the duopoly entry-exit game, where I have a state vector that's endogenous, and I also have the evolution of the state vector depends on some exogenous shock. So the state vector has a number of active firms, 0, 1, 2, because we have two firms on the same market. They can both choose not to enter or not to enter. And the firms will observe this productivity shock for each of them, and some exogenous shock. And then the transition, if you're standing at the angle of firm 1, the transition matrix, if you take action, enter or exit, looks something like this. So it looks like a Heidelman structure where each block has a different CCP characterization. And this, if you take the difference of this two, that purely depends on your luck. If you can have that F2 does not alter the null space of F tilde. So we cannot rely on that. So we look at the two-period finite dependence, and turns out this game also satisfies two-period finite dependence. So that's something that we can expand the model. And if you might ask, is there any case that two-period finite dependence is not satisfied? Is this model that good? And yes, we do a simulation here. Okay, so so how I do this exercise is that I form like a 4x4 state transition, and I just randomly throw some of them away, and also assign random values to each of the grids. And here's a super arbitrary example that I come up with does not show two-period finite dependence. So you have like first state is a transitory state, second state is absorbing, and for the third and the fourth states, you have like a different probability. And it turns out this structure does not satisfy two-period finite dependence. And I asked ChatGPT, what does it mean economically? Basically give me some super artificial interpretation of this structure. So what I'm saying is that even I have like tried this multiple times, it turns out as long as you have transitivity for most of the states and with some very non-rigorous non-sparsity condition, then two-period finite dependence will hold. So I'll conclude now and leave more time for the next speaker. Thank you.
My name is Takeshi Kasawa, and thank you for having the opportunity to present my paper. And today, I'd like to present my paper titled Sequential Algorithm for Structural Estimations with Equilibrium Constraint. First of all, sequential estimation with equilibrium constraints are prevalent in economy. In general, such kind of estimation problems can be specified by this constraint optimization problem. Here, theta represents main structural parameters, and y represents nuisance parameters or economic variable. And in this problem, Q theta y represents statistical objective function, such as -1 times the likelihood or JMM objective. And gy theta equals 0 corresponds to the constraint based on an economic model. And we can think of many examples. And the first example is dynamic discrete choice models and games, DDC models and games. And in these models, value functions or CCPs correspond to y. And the second example is static and dynamic PLP. And in these models, mean product utility corresponds to y. And finally, general equilibrium models are other examples. So far, probably a widely applied approach will be the nested fixed point algorithm, NFXP. And concerning the NFXP algorithm, first in the inner loop, given structural parameters theta, we solve for by theta such that g by theta equals 0. And in the outer loop, we search for theta star, minimizing the objective function, the q theta y theta. And so far, efficient implementations of the NFXP algorithm have been investigated by many studies, like these papers. And sometimes they work very well. But in other cases, sometimes NFXP algorithm is not very fast. And so in these days, researchers consider more and more complicated structural models. And sometimes they use large data sets. And so the problem of computational cost is very serious. And this is an obstacle to further economic analysis. And the alternative to NFXP is a sequential estimation approach. And basically, in this approach, we sequentially update theta and y. And so far, several kinds of sequential estimation estimation methods have been proposed. And the examples are NPL, APLP, and EPL. And under a property called zero Jacobian property, the limiting point of this iteration coincides with the NFXP estimator. And previous studies have shown that the statistical convergence property of EPL and NPL. And previous studies have shown good performance concerning these methods. However, their performance and applicability rely on the specific structure of the structural model. Concerning the NPL, basically it works well in single agent dynamic discrete choice models, but it is not clear whether the idea of NPL is also applicable to other kinds of structural models. And concerning the EPL, basically its performance crucially relies on the linearity of g by theta with respect to theta. And so in this study, first, I investigate the convergence property of sequential algorithms with zero Jacobian property that we call ZJP. Basically, I generalize the discussions in these two papers. And I show that if we consider MLE or GMM, then first we show first, near quadratic local convergence in large sample, even when initial consistent estimate of theta and y is not available. And if initial consistent theta and y is available, then we can obtain asymptotically efficient estimator even after one iteration. And to derive these two results, the property that the gradient of Q with respect to y is equal to large OP n to the power of -1/2 is a key, where large n represents the number of samples. So by relying on this property, it's not very difficult to derive these results. And yeah, in addition to this theoretical analysis, I also propose a sequential novel algorithm, which I call sequential linearly constrained algorithm, SLC. And this algorithm is applicable to broader structural models. And here, I show the advantages of the proposed SLC algorithm. And I compare the SLC with several kinds of previous methods. And Compared to NFXP, basically it is robust even under the existence of multiple solutions of G by theta equals 0. And as I show later, SLC can be several times faster than NFXP in some dynamic models. And compared to NPEG, namely a Lagrange multiplier based approach, the SLC can be implemented without explicitly computing the Jacobian matrix. The Jacobian matrix of G with respect to Y. So basically, the Jacobian matrix can be high dimensional, especially when the dimension of the nuisance parameter Y is very large. And so just to compute the Jacobian matrix, sometimes it requires a large memory or computational time. And so avoiding explicit computation of the Jacobian is sometimes very useful. And compared to the method, basically the SLC algorithm is applicable even without consistent initial Y, and usually it is robust even in small samples. So here I show a general form of the sequential algorithm. In this algorithm, first we set initial values gamma 0, which is a pair of theta 0 and y 0. And then we iterate the following. And first, in the first step, we compute the value of theta k plus 1 by solving this unconstrained optimization problem. Here, I define objective Q tilde, and Q tilde is defined like this. And in this step, I introduce mapping epsilon, and epsilon is a function of theta given gamma k. And after the first step, in the second step, we compute the value of large yk plus 1 by substituting the value of theta k plus 1 into epsilon given gamma k. So far, several forms of epsilon theta gamma k has been proposed. And these are examples. And we can easily show that they satisfy these three conditions. Concerning these conditions, the most important one is the second one. So the second one is sometimes called zero Jacobian property. And the second condition implies that if gy theta equals 0, then the Jacobian of the derivative of epsilon with respect to gamma is equal to 0. So this is a zero Jacobian property. And under these conditions, the solution of the original constraint optimization problem is a fixed point of this iteration under moderate conditions. Next, we consider local convergence speed of the sequential algorithms with CJP around the solution of the constraint optimization problem. So concerning this, we can derive this formula. So on the left-hand side of this formula is a distance between gamma k and gamma star. And concerning the right-hand side, if the gradient of q with respect to y is close to 0, then the first term, or we can ignore the existence of the first term, and the second term remains. So in this case, we can show this, and it implies that the iteration attains a near quadratic convergence. Yeah, so to derive this, we have not discussed anything about statistical properties or any structures of the structure model. But in statistical settings, MLE and GMM, we can show that the gradient of Q with respect to Y is close to 0 in large sample. So concerning the gradient of Q with respect to Y, we can show this, or MLE and GML. And concerning this property, we can give an intuition. So in large samples, basically MLE and GMM are equivalent to solving this constraint optimization problem, where Q theta Y takes a non-negative value, and the value of Q is equal to 0 at the true value, or the solution of this constraint optimization problem. So here I show a figure corresponding to this situation. And from this figure, we can easily see that the gradient of Q with respect to Y should be equal to 0 because of the first order optimality condition. And regarding this, concerning the MLE, as is well known, MLE is equivalent to minimizing the Kullback-Leibler information criterion, KLIC, and generally KLIC takes a non-negative value, and the value of KLIC should be equal to 0 at the true value when the model is correctly stressed. And in the case of the GMM, generally GMM objective takes a non-negative value, and the value of GMM objective is equal to 0 at the true value, as long as the model is correctly stressed. So in that sense, MLE and GMM can be formulated by this problem. And so that's why this condition holds in large sample. So using the property, we can show statistical and computational efficiency of the sequential algorithms with GZP. And here, we assume that the NFXP estimator, namely the solution of the constraint optimization program, satisfies this asymptotic distribution. And then, first we consider the case where initial consistent estimate of gamma 0 is available. And in this case, we can show that theta k satisfies this asymptotic distribution. So this implies that the sequential algorithms with GJP GJP's estimator attain the same efficiency compared to NFX. And we can also show this property. And to derive this result, basically, root n consistency of initial value gamma 0 is not required, unlike Tiering and Premise 2025. And regarding this point, Kasahara and Shimotsu 2008 have shown that root n consistency of initial value is not required in the context of the MPAO or single agent TDC. So my result is consistent with their result. And next, we consider the case where initial consistent gamma 0 is not available. And in this case, we can derive this. So it implies near quadratic local convergence in large samples. And to derive this result, we use the property that the gradient of Q with respect to Y satisfies this, and the property of GJP, or sequential estimation. So in this study, I propose a new algorithm, which I call SLC. In the case of the SLC, we alternatively use this mapping, epsilon. And yeah, so in the case of the sequential algorithms, basically we need to solve unconstrained optimization problem like this. And this optimization step implies that given a candidate value of theta, we need to compute the value of epsilon. So the computational cost of epsilon should be small as much as possible. And concerning the SLC, so you may notice that there are two types of vectors, this one and this one. And concerning these two vectors, they can be thought of as solutions of linear equations. And generally, solving linear equations are sometimes computationally demanding, especially when the dimension of the problem is large. However, in the case of this mapping, so these two vectors do not directly depend on the value of theta. And so it implies that we can completely compute the value of two vectors before the optimization step. And so in that sense, we can largely reduce the computational cost, and SLC is computationally much less costly. And basically, SLC is closely related to EPL that I mentioned before. And SLC coincides with EPL if the constraint function g by theta is linear with respect to theta. And concerning the SLC, we can easily show that SLC is equivalent to sequentially solving this constraint optimization problem. So regarding this problem, the objective corresponds to Q, the original objective, but the constraint, this one, is a linearization of g by theta equals 0 around large yk and theta k. So that's why I call the proposed algorithm as SLC, sequential linearly constrained algorithm. And aside from computational advantage, there is an additional good property. That is, the direction of the update is a decent direction given an L1 norm merit function defined by this. And concerning this, generally, the solution of a constraint optimization problem is a local minimizer of this type of merit function. And this implies that smaller value of this merit function is desirable from the viewpoint of numerical optimization of the constraint optimization problem. And by utilizing this property as a decent direction property, it is also possible to show global and local convergence results by introducing a line search procedure. But please note that even without a line search procedure, usually the SLC algorithm converges. So concerning the SLC, as you may notice, the Jacobian term, the Jacobian of G with respect to Y appears. And sometimes computing the Jacobian matrix is not desirable, especially when in Y, namely the dimension of Y is large, it can be high dimensional. Generally, such kind of matrix is N1 times N1 dimensional. In that case, it requires large memory storage and large computational time. In addition, to compute the value of the Jacobian, maybe we need to manually derive the derivative. And especially when we consider complicated structural models, it is not desirable. But concerning these points, we can avoid explicit computation of the Jacobian matrix by relying on Jacobian free approach based on Kirchhoff method. So basically, Kirchhoff method is a solution method of linear equations. And Kirchhoff method the packages of Clearlock method is available in many programming languages. And so the implementation is not very difficult. So next, to show the performance of the proposed SLC algorithm, I conducted two types of numerical experiments. In this experiment, I compare NFXP and SLC. And we consider two models. And the first model is a dynamic demand model. Sometimes such kind of model is called dynamic VLP because this is a dynamic extension of the static VLP model. More specifically, I consider a model of perfectly durable goods. And in the model, random coefficients, price endogeneity, and forward-looking decisions of consumers exist. And the second model we consider is a dynamic game with time-varying unobserved heterogeneity. And more specifically, I consider a dynamic entry-exit game. So this is a result of the setting of dynamic demand. And here I show, I compare the computational time of the SLC and the NFXP. As you may notice, the computational time of the SLC is much smaller than the NFXP. So such kind of large reduction in the computational time largely comes from the relative size of the computational time of G, function G, and function Q. To evaluate the constraint function G, it takes about 0.0070 seconds. But to evaluate the objective function Q, it takes only 0.0021 seconds. So regarding SLC, as shown here, the number of evaluations of G is much smaller compared to the case of the NFXP, even though the number of the evaluation of Q is larger than the case of the NFXP. So that's kind of relative size of the evaluations of G and Q leads to large speedup. And the next table shows the case of the dynamic game, and we can see a similar result. And finally, sequential algorithms with GJP is closely related to Neyman orthogonality. And recent studies have proposed estimation methods utilizing Neyman orthogonality or statistically efficient structural estimation. And concerning sequential estimations with GJP, first, Neyman orthogonality holds in the case of the MLE, and even in the case of the GMN, Neyman orthogonality holds asymptotically. And these results imply that the first order condition of this unconstrained optimization problem that we need to solve in the sequential algorithm will be rarely affected by the nuisance parameter gamma k. And so it will lead to a locally efficient and stable estimation in the sequential algorithms with GJ. So finally, let me conclude. In this study, I have investigated convergence properties of sequential algorithms with GJP, such as NPL or single agent EDC, ABLP, EPL, and SLC. And I show that the algorithm attains a near quadratic convergence in large samples, or in the case of the MLE and GM. And when initial consistent values of gamma, theta and y is available, then the sequential algorithms with GGE use asymptotically efficient estimator, even after one iteration. And even when initial consistent values of theta and y are not available, it can work, the sequential algorithm can work as an algorithm to solve this constraint optimization problem. And in this study, I also propose an algorithm which I call SLC. And concerning the SLC, a Jacobian free approach is available. And so in general, we don't have to, if we apply the Jacobian free approach, we don't have to explicitly compute the Jacobian of G. And as I shown before, SLC can be several times faster than NVX in some dynamic model. And so in that sense, I think that SLC can be a practical alternative to NFXP or NPEC, Lagrangian-based NPEC in broader structural models. But please note that, so in the case of NFXP, if computationally efficient inner loop is available, then sometimes NFXP is very fast, and you don't have to rely on such kind of problem. But if the computational cost of the inner loop of NFXP is very large, then this type of algorithms are very useful. Yeah, that's all for my presentation. Thank you for listening.